In the previous section, to demonstrate Euler's Totient function using infinite descent, we presumed that u is the biggest power of p that divides the binomial coefficient p raised to k minus 1, choose m times p raised to k minus u minus 1. This section seeks to validate that assumption, or at least provide strong evidence to support it. We will apply Legendre's formula and also present a more straightforward and intuitive alternative approach. Legendre's formula gives us the exponent of the largest power of p that divides n factorial, where that function in the summation that involves n over p raised to I is the floor function, that is, the integer part of that fraction. So for applying Legendre's formula in the binomial we dealt with in the previous section, we need to apply it on the factorials of the numerator and denominator. Let's better see an example. So let's apply Legendre's formula for binomial 5 raised to 4, choose 3 times 5 raised to 4 minus 2. After computing Legendre's formula for the 3 factorials, we find out that 2 is the largest exponent of 5 that can divide that binomial. Here, u equals 2. So let us see what happens for other values of u. When u equals 3, then Legendre's formula gives us 3 as the largest exponent of 5 that divides the binomial, whether m equals 1, 2, 3, or 4. That is, all possible values. When u equals 2, then Legendre's formula gives us 2 as the largest exponent of 5 that divides the binomial, for all possible values of m. Note how the formulas in yellow and light green apply. Press pause if needed. The same happens when u equals 1. Legendre's formula gives us 1 as the largest exponent of 5 that divides the binomial. Note how the formulas in yellow, light green, and purple apply. By substituting the previously mentioned formulas, we observe that when computing Legendre's formula, the value of m doesn't alter the final result. By applying Legendre's formula, we illustrated in the previous examples that indeed u is the largest exponent of p that divides binomial p raised to k minus 1, choose m times p raised to k minus 1 minus u. However, when attempting to prove this finding, we encountered some challenges. We can at best deduce that the biggest exponent of p that divides binomial p raised to k minus 1, choose p raised to k minus 1 minus u, is also the biggest exponent of p that divides binomial p raised to k minus 1, choose m times p raised to k minus 1 minus u, that is, involving m this time. To advance this investigation, we will now introduce an alternative approach to calculate the largest exponent of p that divides the binomial coefficient. This method will enable us to delve deeper into the topic. To determine how frequently p divides the binomial coefficient, we must calculate the number of times p divides each factorial. This calculation is essential as we are considering the scenario when the greatest common divisor of p raised to k minus 1 and I equals p raised to omega. Before delving into formulas, let's explore an example to understand how multiples of p are distributed across the range from 1 to p raised to r. As you can check in the table, the sum of the exponents of 5 comprises 4 for 5 raised to 4, which appears one time only, 3 for 5 cubed, which appears 5 minus 1 times, 2 for 5 square, which appears 5 minus 1 times 5 times. They show up 5 minus 1 times within the 5 ranges of 5 cubed. And lastly, 1 for 5 raised to 1, which appears 5 minus 1 times 5 squared times. They show up 5 minus 1 times within the 25 ranges of 5 squared. Adding them together, we find that the sum of the exponents is 156. The computation above is for multiples of p within p raised to r factorial. Should we wish to extend this computation for factorial of m times p raised to r, the result simply adds up m times the great block we analyzed before. So it is m times the multiples of p within p raised to r factorial. There you have an example to illustrate what we just discussed. So the general formula is this one. This finite power series can be easily simplified in a few straightforward steps. The derived formula presented below solves the problem for p raised to k minus 1 factorial and m times p raised to k minus 1 minus u factorial. That is, 2 of the 3 factorials involved in the binomial coefficient. Next, we need to compute the multiples of p within the third factorial. That is, p raised to k minus 1 minus m times p raised to k minus 1 minus u factorial. We'll transform the formula established before and examine first the scenario where m equals 1. Let's illustrate this with an example. Press pause if needed. Here is the solution presented clearly. The first thing to notice is that the condition is independent of the value of p. So far, we derived the formula when m equals 1. How to compute them when m is bigger than 1? Well, this is the formula, where we added that negative second term. Returning to the example we recently examined, you can see how it applies when m equals or is bigger than 1. Thus, it can be visualized that the condition is independent of the value of both p and m. Summing up, this is the set of formulas needed to compute the largest power of p that divides the binomial. Combining them and simplifying, we get a Legendre-like formula. Finally, here we apply the new formula for different values of u, showing that u is the largest exponent of p that divides the binomial where the greatest common divisor is bigger than 1. In conclusion, in this third section, we first delve into Legendre's formula to verify if it's true the assumption that u is the largest power of p that divides binomial p raised to k minus 1, choose m times p raised to k minus 1 minus u. By examining examples, we'll confirm this assumption, thereby providing robust evidence to support the infinite descent proof of Euler's Totient function, as presented in the preceding section. However, we encounter a limitation. We are unable to establish that this assertion holds universally. Subsequently, we derived and proved an alternative approach for determining the exponents of p that divides each of the factorials involved in binomial p raised to k minus 1, choose m times p raised to k minus 1 minus u. This method offers greater precision as it doesn't make use of a floor function, and intuition, as it explicitly elucidates the significance of its components. Through the use of Legendre's like formula, which in fact it's a function and not a formula, we gain clearer insight into why u is the largest power of p dividing the binomial coefficient in cases where the greatest common divisor exceeds 1. That's all, folks. Thanks for watching. If you enjoyed this content, don't forget to give it a thumbs up, leave a comment with your thoughts or questions, and share it with anyone who might find it valuable. If you haven't already, consider subscribing to my channel for more elementary number theory content. Stay tuned for future videos by hitting that notification bell so you never miss out. Your support means a lot.